The second topic for today's lecture is going to be about the work over a curve. Before anything, I would like to bring up a formula that we learned from long time ago, maybe from high school in grade 10 or 11, and that formula is work equal to force times distance. So let's write that down. Work equal to force times distance. I am pretty sure that most of you have seen this formula before. Some of you might memorize this formula as W equal to Fs, and that is the same formula. W equal to F times S, and that is the amount of work or the energy it takes to move an object from one place to a new location. And since this is the main formula for today's topic, let's put a box around that. Work equal to force times the distance. Alright, now let's talk about the limitations of this formula that we have right here. First of all, for this formula to work, the distance that we have right here have to be a straight line. So this distance has to be a straight line. Okay, that is the first limitation, and the limitation goes to the force too. It requires force to be a constant value on this calculation. So force right here must be a constant. Okay, so these are the two limitations we have for the formula that we learned in high school. Today we are going to upgrade this formula to be more advanced so that it can deal with more difficult situations in real life. So let's take a look at the upgrades that we want to achieve. First one, we want to upgrade the characteristic of the distance right here. We want this formula to work for the distance that is not a straight line. We want this formula to work with a distance that is a curve in the space. So we want to achieve this. We want to make this distance a curve in space. It can be a curve in two-dimensional space or in 3D. All right? So no longer limited to straight line. Now we want to upgrade the force too. We want this formula to work when the force that is applied to the object is variable, when the force changes along the path. So next upgrade. This formula must work when the force changes along the path. So this, we are talking about variable force. Okay, so two upgrades. Force that is variable and distance that can be curved. And we want to achieve these two upgrades by using the idea of calculus. Alright, so let's take a look at how it's done. I can just give you the formula, but let's take a look at how it's derived, this new formula that we are going to use today. So let's take a look at this example right here on the left hand side. So here we are working with two-dimensional space. Alright. And we are in the presence of the vector field, all these arrows. So we have this vector field, big F, of x and y. Alright, all these arrows represent the force in the space. So by the way, this represents force in space. Alright, now let's assume that we have an object at point A, which is right here. We have an object at this point, this location, this coordinate in the space. And we want to move this object along this blue path to point B. Along this blue path. Alright, okay. Let me try again. Okay, along this path and goes to point B. Alright. So this one right here is point B, and that is the destination of this object. So as you can see here along this path, which is not a straight line. So we are going to call this path, path C. Definitely a curve in space. Path C that we take, not a straight line. And along the path, it experiences force that changes along the way. Let's take a look here. At this point, we have this force. Okay, let's use red for that. All right, and it sort of changes along the way. not just the magnitude, it changes the direction too. Let's take a look at this point. Now it goes down, this goes a little bit on the left, and sometimes smaller, and change direction. So the force is going to change both directions and the magnitude along the way. So there you go, we have this condition. Path that is not a straight line, force that changes along the line. And of course, we cannot use the formula that we had from the high school. We need to upgrade it in order to find the work that is done on this object. Oh, by the way, in the end, we want to find the work equal to what? That is done along this way, along this path. So let's add this one right here. It should be something like this. Okay? Now, let's try to upgrade this formula that we have by using calculus. When it comes to calculus, we like to break things apart. Like we break the area into small pieces. We do some calculation and then we integrate and combine things together. Same with the volume. We break the object into pieces. Find the volume, the volume of each small piece, and then we add them together by using the integration. Now we are going to use the same concept on this path. We are going to cut this path into pieces, infinitely, many of them. All right. So let's try to cut this path into small sections, and let's assume that it's very small. All right. So all these sections, we cut them, and now the final goal is to find the total work along this whole path, right? But we are going to start with just one section. So let's start with this one section right here, the first section, this one. On this section, we are going to find the amount of work done on the object. And we are going to call that differential work. We are going to find this dW on just this one section. All right. And since the final goal is the total work, we are going to do the same for all the sections, infinitely many of them. And in the end, we are going to integrate this dW in order to get the total amount of work. So let's take a look at this new formula right here. All right, total work is going to be equal to the differential work, which is the work done on each small piece, dW. And in the end, we are going to integrate them all along this path C in order to get the total amount of work. All right, that is the idea. Now, we need to know more about this dW right here because we cannot leave it like this. We cannot perform the calculation with this dW because we don't know what that is. So let's try to magnify this differential work into new terms of the new variables. So let's magnify this small section. So first of all, let's assume that this section is so small that this distance right here inside this section, this path right here is a straight line. And we are going to use a vector to represent that. Let's assume that this is a small vector. So let's magnify that vector to be this one. All right. And we are going to call this vector ds. All right. And the length of this vector, the magnitude, the distance, is going to be the absolute value of ds. So this one right here is going to be equal to absolute value of this vector ds. Oh, by the way, since this is the first section, this point right here is going to be a. All right. That is the distance. That is the path. Now we are going to take the force that is applied to this section. Maybe this vector right here. All right. Now let's bring this vector to this magnified version. Oh, by the way, I just magnify this portion right here. Magnify. Now let's bring the force right here. Force vector. Maybe something like this. All right. So we have this force vector in terms of x and y, depending on the location. All right, so we have more information about this differential W in terms of, oh, not yet. We need to express this dW, differential work, in terms of ds and this force vector F, big F. So let's try to find that. Let's try to find this differential work, dW. Okay, let me change that, dW. In terms of these new parameters, ds and f. And we are going to come back to this formula right here. Formula from grade 10 or 11, work equal to force times distance. We can use it right here because we assume this section to be so small. So the distance has become a straight line. All right, as you can see here, this is so small, the distance becomes a straight line. And the force, we assume it to be just a constant because this is a very small point in the space. All right, so we are going to apply this formula, force times distance. But we cannot use F and ds right away because F and ds points in different directions. The first thing we are going to do is to make F, this force vector, to point in the same direction of the distance or the path. So we are going to project this vector F to be on the vector ds. So we are going to project this. Find the shadow of this force vector big F to be the one on the same direction with ds. All right, and this projection of F right here is going to have magnitude equal to absolute value of F cosine theta. All right, and of course we need this theta right here, which is the angle between F and ds. Okay, let's add this. Angle right here is theta, and that's why we have the projection to be equal to absolute F times cosine theta. Now that we have the force in the same direction as the movement of the path, we can perform the calculation of the work on this section, and it's going to be the force, which is equal to the absolute value of F xy, all right, times cosine theta. This is the projected force on ds, times the distance that we take on this section. It's going to be equal to the absolute value of ds. All right, distance equal to absolute value of ds. And as you can see here, with this these terms, it's going to be equal to the absolute value of one vector times the absolute of another vector times cosine theta, which is the angle between them. And what you see right here, this is a dot product between two vectors. So make a note, this is dot product between, all right, force vector F, big F, and distance vector ds. All right, and in the end, this is going to be equal to dot product of F xy, this vector, and distance vector ds. No more absolute value, just the two vectors having dot product between them. All right, so we have this expression of dW in terms of force vector and distance vector. And we are going to substitute this into dW right here. So let's take a look at the formula that we have at this point. So total work is going to be equal to the integration of this dW has become force vector F xy dot, this is dot product, and we have this distance vector ds. Okay, along this path C. Okay, our formula looks a little bit better than before, but we still cannot use this directly because we still stuck with this ds right here. We don't know what kind of differential distance this one is. So we are going to need to further simplify this formula, and we are going to do that by parametrizing the whole calculation with time. All right, so the whole idea is right here. So let's make a note. We are going to parameterize with time. All right, the whole calculation. First of all, we are going to assign all the variable. Right now we have all the variables in terms of coordinates x and y in the space. We are working with location in the space. But now we are going to move to time. So instead of looking at point A as a location in the space, this one, we are going to assign a timestamp to this point A. So we are going to say that this object is at point A when time is equal to small a. So let's assign timestamp to this point A, t equal to small a. And this object is going to travel in the space and reach point B at time equal to small b. So timestamp at point B is t equal to b. Alright, so this whole path is going to get parameterized to be in terms of time. And we are going to use position vector rt for that. So for this one, path C is going to get parameterized by time, and we are going to use rt to represent that. And rt right here is going to range from t equal to a, starting point, and ends at time equal to b, the end point. T must be in between a and b. Alright, so the first thing we did right here to further simplify this formula is to parameterize this ds into drt. So this one right here, we parameterize this and make this in terms of a step in time, dr of t. Alright, so this is a step in space, but in terms of time. Now that we have decided to work on this time variable, we cannot stay at x and y variable for the force vector. We need to transform this force vector to be in terms of time too. So the next thing we are going to do is to transform this to be force vector in terms of time. So this has to become this force vector in terms of time. Okay, so you can make a note right here that transform all vectors to be in terms of time, to be in terms of t. Alright, so we change f, we change ds, and let's take a look at the new version. So this is going to be equal to integration of f in terms of time. Now, dot with this dr right here in terms of time. Now everything has become new terms in terms of this new variable time. But we are not going to stop here. We are going to add some more term. So we are going to divide this drt with dt. And to balance this division, we are going to multiply it back times dt. Alright, so in the end it's the same term. But we are going to group this together, these two. Alright, so let's take a look here. Inside this box we have a dot product between a force vector in terms of t and the first order derivative of r with respect to t, which is this term. And we are going to perform the integration of this whole box with respect to time. And now that we work on time, we know the limit, the boundaries for time, and it starts from a and ends at b. So this integration starts at time equal to a and ends at time equal to b. And there you go. Everything right now is in terms of time. Just one variable to consider. Now let's summarize the new formula that we have today. So now total work equal to integration of this dot product, force vector in terms of time, and the first order derivative of r, position vector in terms of time with respect to time. Alright, and then we are going to integrate this with respect to time in the end. Time starts from a and ends at b. Okay, let me fix this one. So t equal to a right here. And now let's put a box around this new formula, upgraded formula. Okay. Alright, so we have an upgraded formula right here, and this formula can work with the distance that can be in any shape. Can be a curve, can be a straight line, and it can deal with the force vector that is variable, that can change along the path. Now that we have this new formula, let's try this formula on one example in the next slide. So let's move to this one right here. In this example number 3, we are supposed to find the work done by this force field. So this is going to be about the work done by this force field. Now let's take a look at the information we have for this force field. First of all, it has 3 components, I, J, and K. So definitely this is a force field or a vector field in 3-dimensional space. So let's write this down. This is a vector field, force field F, big F, of X, Y, and Z. As you can see here, each component is represented by 3 variables, X, Y, and Z. So we see Y here, X here, and Z here. And now this force field is going to be applied to an object, and it's going to move along a curve, and we have the curve right here. And we have this R of t, so it's going to be a position vector in terms of time already. So that is good. So we have this curve R of t in terms of time, ti plus t squared j plus t cubed k. Now this is good because this curve right here has been parameterized with time. So let's make a note right here. This curve has been parameterized with time variable only. So we only have time in this R. And time needs to range from 0 second to 1 second. So this is the last information that we need. And this is it. We can use these informations to find the work done by this force field. So as you can see here, the force is not going to be constant along the path. As you can see here, force is different at each x, y, z in the space. And the curve that you have right here is definitely not a straight line. So we are going to need the upgraded version of the formula that we just derived in the previous slide. So let's bring that formula back here again. So the work done along the path, all right, the upgraded formula is going to be this one. Integration of a dot product between a force vector in terms of time. All right, keep this in mind. This force has to be expressed in terms of time. This force vector. Dot product with the first order derivative of r with respect to time. First order derivative of r in terms of t with respect to time. Once you have this dot product, we are going to integrate this with respect to time. All right, and time starts at some value, t equal to a. We already know what that is for this problem. It's going to start at 0 and ends at b. For this problem, it's going to end at t equal to 1. All right, so we need this formula. Now let's take a look at the information that we have. Let's start with the curve. So we have this parameterized curve in terms of time. So this vector, position vector rt at different time is going to be equal to ti first component plus t squared j second component and last component t cubed k. So what you see right here represent the curve in the space. So each component, by the way, let's make a note right here. This represent the curve in space. Represent curve that we need to take in space. Which means that each component of this RT is going to represent the coordinates in the space. All right? Each component represents coordinate in the space. So let's take a look at this one right here. First component for I is going to represent x coordinate in the space. So this one right here is going to be x coordinate along the line. All And this one right here represents the y coordinate along the line. And last one, this t cubed is the z coordinate along the path. So now we know that along the line we have these relationships. So let's make a note right here that along curve x is going to be equal to, let's use blue right here. X is going to be equal to t, alright, x coordinate. Y coordinate is going to be equal to t squared, coming from this second component right here. And that is the first component and last component. Z coordinate is going to be equal to t cubed. So we are going to stick with these relationships along the line between x and t. T cubed. Alright. Now let's take a look at the force field that we have. So we have this force field in terms of x, y, and z. So let's bring all the terms right here. It's going to be equal to y minus x squared, I, plus z minus y squared, j, plus x minus z squared, k. Right, as you can see here, in order to use the formula that we have, we are supposed to have the force vector in terms of t. Okay, let's take a look at the formula right here. Force vector has to be in terms of t, but right now it's in terms of x, y, and z. So we are going to need to transform this force vector to be in terms of time. And we are going to use these relationships that we built earlier, this one. Alright, x equal to t, y equal to t squared, and z equal to t cubed. So it's going to go down here. Equal to, alright, y equal to t squared. So new terms, t squared minus x squared, x equal to t, so we have t squared right here. Alright, so that is the first component in terms of t. Now z equal to t cubed. So new terms, t cubed minus y squared, y equal to t squared. So we have t to the fourth right here. Alright, and that is the second component, j, plus, and x equal to t. New term, minus z squared, z equal to t cubed. Z squared is t to the power of 6. So we have t to the power of 6 right here. Okay, and that is the last component. So there you go. Now we have this force vector in terms of time only along this path. Alright, so let's take a look here. T squared minus t squared, this is going to be equal to 0. Alright, so we have this ft. Now we need this term. First order derivative of r with respect to time. So we need to diff this r right here in with respect to time. So let's find that. dr of t with respect to time. So we need to diff each component separately. So I diff the first component right here with respect to time. I get 1, so it's going to be 1i, just I. Alright, diff this second term with respect to t, I get 2t. So I have this plus 2tj. Alright, and then I need to diff this last term, last component, with respect to time, and I get 3t squared. So last component for this dr by dt is going to be 3t squared. Okay. Alright, so we have this big F in terms of t right here, and first order derivative of r with respect to time right here, and we need to perform the dot product between them. So let's do it right here to save some space. Alright, so this is going to be equal to, we want to find this f of t dot with dr of t with respect to time, and it's going to be equal to, let's take a look at the first component. First component right here is equal to 0, so it's going to go to 0. Second component, product between this and this is going to be equal to 2t of t cubed minus t to the fourth. And then we find the product of this third term and with this one. So add that to here. It's going to be, sorry for the space, 3t squared times t minus t to the power of 6. And there you go, we have the dot product between f and dr dt. Alright, so let me fix this one. This is supposed to be just plus. Okay, and now we need to integrate this with respect to time from time equal to 0 to time equal to 1. So it's going to be this right here. So work is going to be equal to integration of f dot dr dt. So we have this 2t. So I'm going to multiply this inside. So I have this 2t to the fourth, 2t to the power of 4, minus 2t to the power of 5. Alright, plus next term. This goes in. So this one goes in and goes in here too. So I'm going to have this 3t to the power of 3 minus 3t to the power of 8. Alright, and I'm supposed to integrate this dot product with respect to time, starting from time equal to 0 and ends at time equal to 1. Once again, what you see right here. What you see right here is f dot dr dt. Alright, so let's integrate this. It's going to be equal to, first term, this is equal to 2t to the power of 5 over 5 minus 2t to the power of 6 over 6 plus 3t to the power of 4 over 4 minus 3t to the power of 9 over 9. And we need to evaluate this at two values of t equal to 0 and t equal to 1. So this 1 goes in here, here, and here. So we get this 2 over 5 minus 2 over 6 plus 3 over 4 minus 3 over 9. And we are supposed to put this into 0. And as you can see here, 0 goes in, everything goes to 0. So we don't need to worry about that. And we just need to calculate these fractions. And in the end, we are going to get this term, 29 over 60, as the answer for this example number 3, the work done by this force field along this curve.